So we'll continue with our topic, subsystem design. So in subsystem design, we are going to study about multiplier. So as you know, subsystem design at VLSA level is considering two parameters, data path and hierarchy. So any design at IC level must be analyzed in terms of its hierarchy, top-down design methodology, and its subsystems. And all the subsystems must be optimized for three entities: less area, low power, and high speed. And we have seen the subsystems shifter. From shifter, we have covered barrel shifter, then an adder. So a half adder adding 2 bits, a full adder adding 3 bits, an input carry and 2 bits. And using a full adder, we have studied about uh, 4-bit full adder implemented as replicary adder, carry lookahead adder, carry select adder, carry skip adder. So these are the four methods. In first replicary adder, we have seen that there was a delay created due to carry propagation. In order to eliminate that, in order to speed up the carry computation, we have gone for alternate method like carry skip adder, carry select adder, carry lookahead adder, where generate and propagate bits are used. So you know generate bit is nothing but product of 2 bits. Propagate bit is nothing but XOR of 2 bits. So once carry was propagated, carry was generated, it was propagated based on these bits. Sum and carry were designed, and from that we have three adders, 4-bit adders: carry skip adder, carry select adder, carry lookahead adder. So after that, the next subsystem we have covered was a parity generator. So parity generator generates a parity bit. Along with the message, we are going to append this parity bit, and it is even parity means the parity bit is selected such that it is having even number of ones. Similarly, you can define odd parity. Then we have seen ones and zero detector circuit, where the number of ones and number of zeros in the input message are detected. Then the comparator, where the both inputs are compared, and it is, if they are equal, it is an equality comparator. If one of them is greater than and another is less than, it is your magnitude comparator. So magnitude comparator was having three outputs: A greater than or equal to B, A less than or equal to B, A equal to B. Then one more design we have covered is ALU. So we have to see that arithmetic logic unit is the implemented as a data path architecture along with input output blocks, registers, shift registers, and ALU implemented as a 1-bit adder. So if you have seen, 1-bit adder was acting as a full adder, 1-bit adder was acting as a subtractor, it was acting as an XOR gate, XNOR gate, AND gate, and OR gate. So after covering this all the topics, we are left over with two topics. One is multiplier, another is counter. So coming to multiplier, multiplier is a combinational circuit where two binary numbers are multiplied. Okay, so we are going to multiply two binary numbers, and it is a multi-bit. So if you multiply two integers or any value, it is represented in binary form. So a m-bit value is multiplied with an n-bit value. So if you see, it will be having n rows. So your multiplicand is capital M, multiplier is capital N. If you multiply each multiplier bit with a multiplicand, it will be having n rows, capital N rows, and the size of each row will be m bit. And so each multiplier bit multiplied with a multiplicand produces product term, partial products. These partial products are added to get the final sum, and this final sum will be having number of bits is equal to m plus n. So this is what we covered in earlier topic. So now we will continue with our multiplier. So multiplier, if you multiply in your elementary method, each bit of your multiplier with its multiplicand, its multiplicand, you are going to get partial products, and these partial products are generated row wise, and the next row it is shifted to one bit left, and finally they are added by a full adders and half adders. So then you are going to get a sum, and where you are using a full adder and half adder, such design is called an array multiplier. So we have an array multiplier for multiplying two unsigned bits, unsigned numbers, and for signed numbers we are having Booth algorithm. So we will continue with our unsigned array multiplier. So if you see two unsigned binary numbers A and B, each of m and n bits, so capital N is size. If m can be n, okay, then in such a case, like m and n can be same. Okay, example, you can take m as 6, n as 4. So a 6-bit value you want to multiply with a 4-bit value. So how you write its how you write its how you write its uh, decimal value is, you have to multiply each of the bits of the binary number with its weight. So how weight is brought? Weight is brought by 2 power of its position value. So that's why A can be written as sigma I equal to 0 to m minus 1 ai into 2 power of I. That is capital A. Another B is equal to sigma Z is equal to J equal to 0 to n minus 1 Bj into 2 power of J. So these are two numbers in terms of its representations. And what is the multiplication? Multiplication product term is nothing but A cross B, which is written as sigma I equal to 0 m minus 1 into sigma J equal to 0 n minus 1 ai into Bj into 2 power of I plus J. So this is the mathematical notation. Based on this only, your final product term, if m is equal to 6, n is equal to 4, so total product term, after you make it product, you are going to get final value as a bit value of 10. So P9 to P0. So those values can be written as sigma I equal to 0 m minus 1 into sigma j equal to 0 to n minus 1 ai bj into 2 power of I plus j. So that is related to the product term. So this is an array multiplier because we are going to use full adders and half adders in this. So how we are going to implement with an adders, that we study with one example of its multiplications. So here left side we have a multiplicand, right side we have corresponding mathematical notations. So if you see A3, A2, A1, A0, B3, B2, B1, B0 are two numbers to be multiplied. The first one is called multiplicand. The second one is called multiplier. When you multiply each bit of your multiplier with a multiplicand, B0 multiplied with first multiplicand gives A0, B0, A1, B0. So we should be going on writing from LSB to MSB. So A2, B0, A3, B0. In the next row, B1 is multiplied with A0, B1 is multiplied with A1, B1 is multiplied with A2, B1 is multiplied with A3. So that is again written by moving one bit left. Okay. So, and the third row, we are going to multiply B2 with A0, B2 with A1, B2 with A2, B2 with A3. So finally, A0, B0 is written as some the final term B0, but whereas A1, B0 plus A0, B1 must be summed by using an adder. So there are two bits. A1, B0 is one product term. It is one value. A0, B1 is another value. So they are summed. So you are going to get P1. In the third case, you will be getting P2 by sum of above 3. But not only sum of above 3, you are going to get a carry from the previous stage. So here it requires that the output is represented as P7 to P0. So first one is we are going to generate partial products. Next one is partial products accumulation. Next is final summation. So this multiplication is represented on the left side using an example where the multiplicand is 1101 and the multiplier is 1001. Now you are going to multiply the each bit. 1101 multiplied with 1 is written as 1101. By moving one bit left, 0 is multiplied with 1101, you are going to get 0000. Then again 0 is multiplied with 1101, so again it is 0000. Then 1 is multiplied with 1101, so again it is 1101. Now in the LSB side, 1 is written as 1, 0 plus 0 is 0, 1 plus 0 plus 0 is 1, 1 plus 0 plus 0 plus 1 is 0. Carry is sent to the next stage. So where 0 plus 0 plus 0 plus 1, it is 1. Then 0 plus 1 is 1. Final one is 1. So in the design, in the fourth column, you got a carry generated, which was written in the third column as 1. So this is related to the multiplication of two numbers using our basic method. And for this, we have to design a hardware which can do this computation. So remember, we have partial product generation, partial product accumulation. So based upon the design requirement, unsigned array multiplier requires that you have to multiply each of your multiplier bit with multiplicands. So that's why there are 4 rows representing the multiplier bit, and corresponding AND gate inputs are multipliers like A3, A2, A1, A0. The first topmost row is B0. So B0 is multiplied with A3, A2, A1, A0. Next, B1 is multiplied with, so you can see in the left side diagram, our A3, A2, A1, A0, B3, B2, B1, B0 are written and corresponding outputs are shown. It is the same thing in terms of an array multiplier is this design where we are going to write row wise its values, and we have to decide where a full adder and half adder is required. So this square box represents it is a adder. So you can see for the both, for all the AND gates, we are going to write each row. Each row is B0, B1, B2, B3. B0 is multiplied with multiplicand. So multiplicand values are A3, A2, A1, A0. Next, B1 is multiplied with A3, A2, A1, A0. B2 is multiplied with B1 is multiplied with A3, A2, A1, A0. Okay. So again, B2 is multiplied with A3, A2, A1, A0. B3 is multiplied with A. So for each multiplication, we are showing with an AND gate. Okay. And if you see, as our elementary method, we have to shift one bit. So that shifting is also shown for this gates. That shifting is also shown for the gates. Then first one, A0, B0 is multiplied, and that is directly fed to the output. Whereas in the second column, you have one row as A1, B0. Another row we have A0, B1. Okay. So A1, B0 multiplied value and A0, B1 multiplied value must be added. So you require 2 bits to be added. So you require a half adder here. So, but if you see the third case, you have A2, B0. Okay. A1, B1. A1, B1. and A0 B2. So you have to add 3 bits. So you require a full adder. So based upon this analysis, you can see the diagram. On the right side, we are going to select where you have a required for full adders or half adders. So you can see finally the requirement A0 B0 is sent as P0. A0 B0 is sent as P0. So first row is generating A1 B0. Second row is generating A0 B1. That is spread with an yellow color. If you see, this yellow color line is telling that A1 B0 and A0 B1 are sent to an adder. Okay, this okay. So each of the product terms are sent to certain adders, and that requirement is written here as A0 B0 is directly fed, it is P0, but whereas A1 B0 and A0 B1 they are added to generate P1. Okay, because they are only 2 bits, we require a half adder. We require a half adder. So A1 B0 plus A0 B1. A1 B0 plus A0 B1. So you can see here A1 B0 plus A0 B1. So they are two product terms. They are multiplied. So we require only half adder. But if they are multiplied, if they are added, there is a chance of getting the carry in that stage. Okay. So the carry can be 0 or 1. So based upon that, you can now represent a horizontal movement telling that from each row, that addition will generate a carry. From each row, the addition will generate a carry, which is fed to the next stage. Okay, which is fed to the next stage. So which is fed to the next stage as. So you can see in the rightmost diagram from half adder, we are representing one yellow line. So it is telling that the sum of A1 B0 plus A0 B1 is generating a carry that is sent to the next stage by this arrow mark, and this vertically output is sent to P1. So P7 to P0 are the final product terms. So now if you see in the third case, A2 B0 plus A1 B0. So you just see the diagram. A2 B0 plus A1 B1. Okay. So A1 B1 plus carry from its half adder will require a full adder. Whereas in the below row, in the third row, you are going to sum only two values. One from output of a full adder, another is A0 B2. So because you require only 2 bits to be added, use a half adder. So in this design, we are going to analyze based upon 2-bit addition, we are keeping a half adder. Based upon the 3-bit addition, we are keeping a full adder. So this is an array multiplier. Array multiplier is a combinational circuit where the m by n multiplication is analyzed in terms of full adders and half adders. So in the third case, if you see here, from full adder, we are pointing one arrow that is carry is propagated to the next stage. So A3 B0 plus A2 B1 plus carry from its next stage. So you require a full adder. Okay, you require full adder. But if you see the final case, so here what we are doing is in the left diagram, we are going to show the number of bits to be added. So your number of bits are increasing more than 2 bits. We are telling that we require a full adder. So here if you see the right side, A3 B0 plus A2 B1 plus carry. See my arrow mark. This full adder we are pointing. This full adder requires A3 B0 plus A2 B1 plus carry from previous stage. So it is a full adder. And here requirement is you are going to get output from this full adder and A1, B2 and also carry from this half adder. So because you require 3 inputs, it is a full adder. But whereas in the final case, when P3 was generated, we are getting output from a full adder and A0 B3 must be added. So that's why it is half adder. So you can just go through that part. In each stages, we are going to decide half adder or full adder based upon the number of bits to be added. And carry is propagating from the LSB to the MSB. So that is represented with this yellow lining. So in this general example, we are deciding this is the A3 B1 plus carry from previous stage. A3 B1 plus carry from previous stage. So you can just analyze this diagram for a certain time. Just analyze it. A3, A2, A1, A0 and B3, B2, B1, B0, they are multiplied and each of the product terms are written and each product term is added to get P7 to P0. Okay. P7 bit can be 0. Okay. So you can see so here when P5 was generated, we are adding 2 bits with carry from its previous stage. So you require a full adder. So wherever 2 bits with carry from previous stage, write a full adder. Wherever only 2 bits are added, see even it is a product of A and B, it is 1 bit only. Okay, it is written mathematical as A and B. But once you go to the binary numbers, it becomes either 1 or 0. So example is giving P6 to P0, M bits are 4, N bits are 4. So N plus M is giving as 8 bits P7 to P0. So this P7 to P0 is finally generated and this you can also analyze. So by its example, so finally it is P7 to P0. So the explanation, if you want to listen, you can listen. I'll switch on from the same position. So we have started with some around here. Okay. The basic method we started here. Now you can listen to the voice. Okay. So you can just analyze once again. So A3, A2, A1, A0, B3, B2, B1, B0 are the multiplicand and multipliers which are done multiplication, and each of the partial products are written, and each partial product is represented with one of the value, like A naught, B naught is 1 here. So when you multiply 1 and 1, you are going to get 1. So A naught, B naught, then A1, B naught, then A naught, B1, like that. We are writing all the rows. Then we are based upon the addition. You can just go through this video once again. Go through that each row. So what is done on the left side, what is done on the right side? Because already the explanation is done now. So you have to analyze that whether you have understood this logic. So that's why just go through the diagram. A3, A2, A1, A0, B3, B2, B1, B0, they are multiplied and corresponding outputs they are written. So these same product terms will be written on the right side. Just go through that. After this, I'll explain it. In the left side, we are going to show our basic example with corresponding notations. So A3, A2, A1, A0, B3, B2, B1, B0 are multiplied and corresponding rows are written. Where is A3, B naught? Where is A2, B naught? Like that. So then they are added. Once we are adding, if it is a 2-bit, we are written with a half adder. If it is a 3-bit, so 2-bit also will generate a carry. 3-bit also will generate a carry. So that carry is there. In the next stage, we are trying to full adder. So like that, we have finally generated P7 to P naught. And this is called an array multiplier. So once you complete this diagram, We'll go ahead. So you can check left side in the example he is covering which three bits are added or based upon that corresponding adders are written. So only in the leftmost side and rightmost side you are going to get a half adders because there only two bits are added. Like you see the last diagonal element, half adder, half adder, half adder. And similarly, almost MSB side, there also you require a half adder. In between you require full adders because you require three bits to be added. Two product terms or carry from its previous stage, or three product terms or and also carry from previous stage. So you have to verify it each stage corresponding p bit and its diagrammatical representation in the hardware. In the hardware, we are just writing in the box whether it is half adder or full adder. So two bits along with carry from previous stage is generating P5. So this P5 on the in the design, it is nothing but a full adder representation. So here two bits are added. One is its bit A3, B3 and along with its carry from previous stage. So this carry from previous stage will generate P6. So that's why you require a full adder. And actually mathematically it is M plus in 8 bits. So that P7 is just 0. Okay, when it's representation. So it can be 0 or 1. That depends upon the carry from this stage. Sorry, I could not analyze. So carry from this stage is P7. So that's why in the diagram, in the hardware, we can see full adder output. Horizontal arrow marks to the left side represent carries. Vertically data moving to the full adder are inputs to the full adders. So this is the same diagram. P7 to P0, 4 by 4 unsigned array multiplier, where green lines will represent multipliers. Vertically, AND gate in other inputs are multiplicands. Each of your adders will receive inputs as product terms, and carry was propagated horizontally by this yellow lining. So how carry will propagate from one stage to another state, that is written as in its yellow lining. So we have studied till now an array multiplier implemented by using a 4 cross 4 array multiplier with full adders and half adders, where our normal m by n multiplication was implemented. So we are going to continue from the same topic, array multiplier, where in this example, we are starting with our 4 cross 4 unsigned array multiplier. So where A3, A2, A1, A0 and B3, B2, B1, B0 are multiplied, and each of the partial products are added vertically. So while adding, if 2 bits are there, we have kept a half adder. Along with 2 bits, if carry is propagated from previous stage, we kept a full adder. So finally, product terms are written as P7 to P0 because m plus n is equal to 8. So m is equal to 4, n is equal to 4. So, and again, n rows. So B3, B2, B1, B0, n rows, and size of column, size of each row is 4 bits. That is m value. So here the topic covered is we have to analyze as carry is propagating from horizontally. The finally output generated is P7 to P0. So there is a delay in its computation. So as the number of bits increases, so this delay propagation will, because carry from has to propagate from first half adder. If you see here, A0, A1 B0 plus A0 B1, they are going to be added and carry is generated here. So that carry is moving to full adder as its input. You are again multiplying 2 input bits with its carry. So again the carry is generated and it is passed to the next stage. So if you see here, we are having a critical path represented as carry propagation through all the gates. So there are two arrow indications. One was with uh, some pink color, another is green, thick green color. So if you enlarge and see the picture, you can analyze it. So that is a critical path. What is the critical path? The values has to propagate through maximum gates. So here the maximum gates counted are 8. If you see this green color line, half adder, full adder, half adder. So from there it is given as input to a full adder. So a carry was propagated. That full adder output is fed to the next full adder, and this next full adder output is a carry to the full adder. So like this, finally P7 is generated. So this green color is passing through 1, 2, 3, 4, 5, 6, 7, 8. So 8 gates, 8 gates, among which full adders are 6, half adders are 2. And the pink color line is passing through half adder, full adder, half adder, full adder, half adder, full adder, full adder, full adder. So finally P6. So there are again 4 full adders, 1, 2, 3, 4, and remaining 3 half adders. So this is the maximum path. Wherever if you see in the entire design, this is the maximum longest delay path. So that is called a critical path. So that is the main requirement to analyze the critical path. So we are considering one more example. So as here we have shown the example, the 4 by 4 array multiplier where critical path is analyzed. This critical path is coinciding at two places, one at the starting part and one at the ending part. So there the signal as to the input values propagated are colliding here. So these two green and pink here, one more green and pink here. So these two critical paths are coinciding at that point. So again, a 4x4 unsigned array multiplier is considered in order to just analyze the critical path. So here a, a general example is considered where three rows are covered with half adders and full adders, and three indications, green color, yellow color, and pink color are shown. These are the critical paths. Pink color is a critical path of both 1 and 2. Okay. And whereas green color is critical path 1. So critical path 1 is starting from full adder to a half adder, next to a full adder, next half adder, next full adder. Okay. Then it will go to again final full adder, but we have written pink color. Pink color tells that this critical path is coming both from yellow line and green line. So that's why there we have written a pink color. So in the first case also, here yellow color carry from your half adder propagates to the left side. Also carry from half adder will propagate to full adder. Then the output is written as a green line. But whereas this carry is propagated as a carry as well as input to the next half adder. So here we have written the critical path 1 and 2, where both critical paths are colliding. So whereas output of half adder is a carry, which is input to your full adder, and that output is nothing but carry to the next stage. But whereas this sum is acting as input to a half adder. So sum is acting as an input to a half adder. So along with some input, this sum is acting as is going to be added and carry is generated. Okay, so that carry is again fed to the next stage as an input. So this is a diagram where we want to cover the critical paths. So here we are going to show yellow lines. So what is this yellow line is critical path 3. So the horizontal paths carry generated are shown with yellow line. So if you see first one, wherever I have written 1, wherever 1 is written, that is one carry. Second one is another carry. Then 3 is another carry. So these are the 3 carries, yellow horizontal lines, and 3 green colors. Okay, 3 green colors. So critical path so they are these green colors are uh, written for outputs of a full adder. So 1, 2, okay, and next 2 pink colors, they are written as critical paths 1 and 2, where both yellow and green are colliding. So if you see the delay of this multiplier is written as 3 yellow horizontal lines plus 2 pink color lines. So it is m minus 1 plus n minus 2 into carry. So where carry is generated is output of a full adder, 1 carry, this pink color, where 2 is written, and another full adder, output this pink color. So if you see here, considering only critical path yellow line, there are 3 carries. So there are 3 carries, one from full adder, 1, 2, 3. So that's why 3 yellow horizontals are represented. So because it is related to oh, this is related to um, multi multiplicants, it is written m minus 1. So it is 4 minus 1 plus n minus 2. N minus 2 because it is n is related to each row. N is related to each row. If n is 4, you have a 4 rows. So the delay is related as n minus 2 because this one and this 2. Okay, this 1 and 2 is written as n minus 2, which is 4 minus 2. So in general, the mathematical equation where so this 1 and 2 are nothing but outputs of full adders. So that is related to delay of a sum. Okay. Whereas this pink color 1 and 2 are the carries of your full adders. So they are related to your T carry. So in mathematical terms, T delay of your multiplier is nothing but m minus 1 plus n minus 2 into T carry plus n minus 1 into T sum plus T into AND gate, because AND gates are the first one which are generating the product terms. So that is the delay of an AND gate plus delay of sum, because that is related to n minus 1 rows. So it is n minus 1 into T sum and plus m minus 1 plus n minus 2 into T carry. So this is related to critical path and its delay in an array multiplier. So here the number of gates utilized will be analyzed. So green color is the critical path 1. Another critical path is yellow color, and where the two critical paths are colliding, that is written with the pink color. We are using 16 AND gates. If you have seen the first diagram, we are using 16 AND gates. You can calculate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. They are 16 AND gates, and full address will count it here only. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 full adders. Okay. In this row, 2 full adders. In this row, 3 full adders. 3 plus 2, 5. In the last row, again 3. 5 plus 3, 8. So you remember 16. It is 16 full adders. Sorry, 16 AND gates, 8 full adders, and half adders are 1, 2, 3 diagonally. Then here 4 half adders. So again we'll go to this diagram. So if you see, there are 16 AND gates. Your m value is 4, n value is m value is m value is 4, n value is 4. It is 16 AND gates, 8 full adders, 4 half adders. Together they become 12. So it is nothing but m minus 2 into n is your full adder count. Number of half adders will be equal to capital N. So in general, if you want to design an m by n multiplier, an array multiplier, the number of half adders will be equal to capital N. The number of full adders will be used is equal to m minus 2 into capital N. What is m? 4. 4 minus 2 is 2 into 4, 8. Okay. So this is the mathematical formula where you can analyze whether your design is correct or not based upon the analysis. What is the analysis? You require totally 16 AND gates, means it is m by n AND gates. M by n AND gates. And it is 8 full adders. It is nothing but m minus 2 into n. And it is n full half adders. It is so the total number of adders required is, what is the total number of adders required? Full adders plus half adders. 8 plus 4 is 12. But how you can get it? The mathematical formula is m minus 1 into capital N. What is m minus 1? 4 minus 1, it is 3 into 4, 12. So that is the design. So you can analyze this delay path. So in m cross n multiplier, so total multiplier equation is m minus 1 plus n minus 2 into t carry plus n minus 1 into t sum plus t AND gate. So each carry is propagated, so the delay is written as t carry. So delay generation in t sum. So just analyze this one. Now I will once again explain the T multiplier delay calculated. Here you can see in the left side I have written 3 yellow horizontal lines, which is 1, 2, 3. So they are lines, yellow lines, critical, and there is 3. Here it is 1, here it is 2, and here this horizontal, if you see, this is an pointed here. So this is 3. So 3 green horizontal lines. So there are 3 horizontal yellow critical paths, 3 green color critical paths. So it is only color indication that there is 2 different critical paths. Yellow color is one critical path, green color is one another critical path. Yellow color we are having 3 critical paths, and green color we are having 3 critical paths. So this 1, this 2, and this 3. Next pink color are 2 because the one here it is 1. Okay, the topmost one, and the next one is where both critical paths are colliding. That is, so based upon this we have written m minus 1 plus n minus 2. Okay, m minus 1 is related to the number of uh, uh, critical paths 3. So it is m minus 1 plus number of critical paths colliding, they are 2, 1 and 2. So n minus 2. So it is related to carry propagation. So that way it is m minus 1 plus n minus 2. Whereas this n minus 1 we are getting, okay, here, and that is because of number of critical paths. The number of critical paths are 2 plus 1. 2 are yellow and green. 1 is pink color. So it is 3. So that 3 you can get it by n minus 1. So n minus 1 will represent number of critical paths, and m minus 1 will tell number of critical paths, 2 different critical paths. So one is This is one critical path, another critical path, another critical path. Green color, this is 1, 2, 3. So critical paths. Whereas n minus 2 tells number of critical paths which are both 1 and 2. So which is pink color? Here, this one, so right side you see topmost 1, 2. So this n minus 2 is related to those which are both 1 and 2. N minus 2 tells it is both which are 1 and 2. M minus 1 tells the number of critical paths of each. So here, this is 1, 2, 3. This is one critical path. Here is 1, 2, 3. The number of paths. So that is M minus 1. So here we have studied the number of gates required as M cross N AND gates. M cross N AND gates, N half adders, M minus 2 into capital N full adders, and M minus 1 into capital N adders. So this is related to your array multiplier. So if you see here, summary, the path between the input to the output with the maximum delay. So because if there are more number of gates, you have a more delay. So the path between the input and output with the maximum delay is critical path, and delay of your multiplier is m minus 1 plus n minus 2. M minus 1 is the number of rows the carry must propagate. So for either it is yellow color or green color, it is m minus 1, it is 3. And where both critical paths are available, they are 2, like pink color, n minus 2. And the number of critical paths are 3, which is n minus 1. And this is gate delay. So number of AND gates are m cross n, number of half adders is capital N, number of full adders is m minus 2 into capital N. Total number of adders we have used is m minus 1 into n. So this is 4 cross 4, 16. Half adders it is 4. Full adders is 4 minus 2 into 4. It is 2 into 4, it is 8. And it is m minus 1 star n is number of adders is 12, which is 8 plus 4, which is nothing but 4 minus 1, 3 into 4. It is 12. So this completes our topic array multiplier. So we'll continue with our next topic, multiplication for signed. Okay. So this completes topic array multiplier.